Have you ever stopped to wonder what is actually happening inside the AI systems that are totally reshaping our world? I mean, really, under the hood. Well, it's been an incredible journey, from these really simple, brittle rules to the powerful learning engines we have today. So let's dive in and see how it all works.
It all really starts with a pretty simple question. A question you could ask a 5-year-old. Hey, what does a cat look like? But for a computer, this turns out to be a monstrously difficult engineering problem. And honestly, trying to solve this one simple thing forced the entire field of AI to completely reinvent itself.
So to really get why that question is so hard, we kind of have to take a look back at how we used to solve problems with computers. It's a story of moving from rigid black and white logic to something much more flexible, something that can actually learn. The first crack at this was, well, it was to just write a bunch of rules. If it has pointy ears, and it has whiskers, and it has fur, then boom, it's a cat. But you can probably see the problem here. This approach is just so incredibly fragile because the real world is messy. What about a cat that's sleeping? Or a cat you only see from behind? Or one that's half hidden in a box? The rules just fall apart and the whole system fails.
So this constant failure forced an evolution. Back in the 70s, it was all about writing rules by hand. Fast forward to the 2000s, and we were still doing manual labor. But this time, we were handcrafting features, things like edge detectors or texture patterns for the machine to look at. Both ways were just so tedious. The real revolution, the game changer, was deep learning. That's when we finally said, you know what, forget all this manual work. Let's let the machine figure out what's important all by itself.
And this led to a total flip in how we program. Think about it. The old way, you gave the computer the rules and some data, and it gave you back answers. With deep learning, you give it data and the answers. Like, here are 1 million pictures of cats, and they're all labeled cat. And the computer gives you back the rules. The machine literally learns to write its own rulebook for what a cat is. So how on earth did we manage to build a system that can actually learn like this? Well, the spark of inspiration didn't come from computer science, interestingly enough. It came from the most powerful and efficient learning machine we know of, the human brain. What we did, essentially, was create a really simplified mathematical version of a biological neuron. The dendrites in your brain that receive signals, those became our inputs. The synapses that control how strong each signal is, we called those weights. And the axon that fires off the final signal, well, that's our output. We basically built a digital brain cell from the ground up. So now we've got these simple little digital neurons. We can start stacking them together, layer by layer, to create a network. Kind of a digital brain. But there is one absolutely crucial component that's still missing, the thing that makes it all work. And that missing piece is something called the activation function. The best way to think about it is like a little gate or a dimmer switch on every single neuron. After a neuron adds up all the signals coming into it, the activation function decides if that combined signal is strong enough to pass on, whether the neuron should fire. This little step is what allows the network to learn really complex, squiggly, nonlinear patterns, not just simple, straight lines. Now, some of the early functions, like sigmoid, were really popular. They do this neat trick where they take any number, big or small, and squash it down to a value between 0 and 1. Super useful for things like probabilities. But they had a fatal flaw when you built deep networks, something called the vanishing gradient problem. Imagine you're trying to whisper a correction down a very long line of people. By the time it gets to the end, the message is so faint nobody can hear it. That's exactly what was happening to the learning signal. It was a massive roadblock. So then came Tanh. It was a slight improvement, centering its output around 0 instead of just between 0 and 1. That helped a bit, but it didn't solve the core problem. That learning signal was still getting lost in the deep layers of the network. And then came the breakthrough, a function called ReLU. And it is shockingly, brilliantly simple. All it does is this. If the input number is positive, it just passes it through. If the number is negative, it just outputs 0. That's it. This ridiculously simple idea fixed the vanishing gradient problem and, as a bonus, was incredibly fast for computers to calculate. This, right here, is what really unlocked the power of deep learning. And finally, there's softmax. This one lives at the very, very end of the network. Its job is to take all the final scores for each possible category, cat, dog, bird, and turn them into a clean set of probabilities that all add up to 100%. This is how the network makes its final call and says with confidence, okay, I am 95% sure this is a cat. Okay, so we've got the architecture.
We have our digital neurons, we've got the all-important activation functions, but how does this whole contraption actually learn to get the right answers? Well, it learns through a really simple, elegant 4-step loop that just gets repeated millions or even billions of times. Step 1, it makes a guess. That's the forward pass. Step 2, it calculates exactly how wrong that guess was. Step 3, it sends that error signal backward through the entire network to assign blame. And step 4, it adjusts all of its connections, its weights, just a tiny, tiny bit to be less wrong the next time around. It's just guess, check, blame, adjust, over and over again.
That third step, backpropagation, that's the magic right there. It's all about assigning blame or credit. When the network gets something wrong, the error literally flows backward, and every single connection in the network gets a precise mathematical instruction on how it needs to change to help fix that mistake. It's an incredibly clever way to tune millions of parameters all at once. All right, so after all of that intense, repetitive training, the model's job changes completely. And this brings us to a really critical difference in the life of an AI model, the difference between training and prediction. See, training and inference are like two totally different worlds. Training is this heavy, two-way street of guessing and then correcting, over and over. It needs a ton of memory and a ton of power. But inference, that's just prediction. It's a fast, one-way forward pass. The model's parameters are completely frozen. It's lean, it's efficient, and it's designed to run anywhere, even on your phone. Now, to put the energy needs of these systems into perspective, I want you to just look at this number for a second. 20 watts. That's the estimated power consumption of the human brain, the most incredible learning machine we know of. The contrast here is just staggering. The human brain runs on the same power as a dim light bulb. Training just one large model like GPT-3 used enough electricity to power hundreds of homes for an entire year. And this enormous energy gap is precisely why engineering for efficient prediction, for inference, is one of the single biggest challenges in AI today. Which brings us right back to the core of it all. As an engineer, why do you need to know about all this stuff? Why do you need to know about activation functions and backpropagation? Why do the guts of the system actually matter? Well, because every single one of those mathematical choices we talked about has a direct physical consequence on the hardware. Understanding the vanishing gradient problem helps you debug a model that just won't train. Understanding how matrix multiplication works helps you spot a memory bottleneck on your GPU. It's what allows you to take this thing that feels like a magical AI black box and turn it into something you can actually build, debug, and make better. And that's really the key takeaway here. Having a deep knowledge of these fundamentals is what separates someone who just uses AI from someone who can build robust, efficient, and reliable AI systems. It turns magic into predictable, solid engineering. And that leaves us with the big, defining question for the next era of AI. As these models continue to grow exponentially, getting more and more powerful, what's going to hold us back first? Will it be our ability to design smarter algorithms, or will it be our ability to physically build hardware powerful enough to run them? The race between software and silicon is on.